What's up, you learners? We're the Gigglers. This is lesson 3.4.
Part 1.
Absolute value functions.
Very good. Okay, you guys can sit down.
Yo.
That was so beautiful. I think I'm gonna get so many subscribers tonight just because how amazing that was. Okay, this, don't let it be a thing. It's my thing now, okay? My turn. All right, we're gonna do this as a do now. It's actually pretty simple. You can talk about it with your shoulder partner. I want you to read it and answer question A, and then I will do B together. If you think you can make a graph, then go for it. But we'll do B together if you can. Okay, so take a second. We're not giggling, we're not chatting. We are working on this, and if you want to buddy up with somebody just to get some ideas, and you can do that. Okay?
Wait, can I buddy up with somebody? I have nobody.
You're alone.
Lathan, you come up here.
Wait, never mind. I'm good then.
Okay. Wow.
I'm just not trying to move.
Okay,
Yeah, you
Can I go to him?
sure, go to him.
Yeah.
But you have to be quiet and you have to focus. If it doesn't work, it'll never happen again.
This is basically your nephew against me.
Oh, you got a pencil?
Take care of your child.
What's that?
You got a pencil?
Yeah, you're gonna write down A, and then if you can draw the graph for B, that would be awesome, but we'll do it together.
Use the Braille marker to determine the number of miles each group of students time to the mile. Yep, pencil.
Focus on my nephew. I'm talking about.
This one's an easy one. You guys come up together.
I want him both done.
So how do you use a marker?
You got it? Okay, good. Just hold on one second. So there's one group at each mile marker.
You need to come in for lunch. She needs to come in for lunch for 3.3.
We've already talked about it. It's her business and my
Just
business.
making sure. I want to make sure
Not
everything's
yes.
fair. I want to
Okay.
make sure everything's fair.
Don't worry. Fair is my middle name. I'm scared because I care. And I'm fair. Fair. Yeah.
Fair?
Yeah.
Is it
Why? I
actually?
think that's not a trade middle name.
I just thought it was a trade name. So called
Because you play fair.
I'm just.
It's not my middle name, but you guys are super gullible.
Wow. My middle name is
Wait, is it like a
Mile? M-I-L-E?
like Miles Morales. My middle name is not Miles. You're so gullible.
Oh!
obviously my middle
All right, you got me.
Needs.
All right, Aiden, do you want to share what you picked up from this?
Yes.
I think they'll be okay.
Like, how can you use the mile markers to determine like how long they need to travel? Well,
Layton, quiet.
well, we can find out the distance between these, and that's how long they need to travel. for example, from 2 to 5, that's 3 miles to get to 5. From 8 to 5, that's also 3 miles. And from 6 to 5, that's 1 mile. And here's where the absolute value of the functions comes in. Because, like, you're going backwards.
Yeah.
You're, like,
He's
going
right, guys. Pay attention to this. This is the really important part. Go ahead.
negative, and you have to find the absolute value of it.
Mhm.
It's like turn negative to positive and leave positive.
That is very good.
And then-
Yeah. Here's your treat.
I've got to learn this.
All right.
I've got to learn this.
There you go. Okay. Good boy. Good job. That was very good. He not only recognized that the distance between these two is 3 miles, the distance between these two markers is 3, but he noticed that the distance from here to here is positive 3. The distance from here to here, he said they're going backwards. So it's really like going backwards 3 or negative 3, but we know that a distance of walking, you can't walk negative 3 miles, right? So what we really are measuring is the absolute value of this distance. So if the difference between 5 and 8, meaning take away 8 from 5, you'll get negative 3. But we need to find the absolute value of negative 3 to find out the actual distance between these. Do you guys understand?
The actual value of any number is just itself, but yeah.
The absolute value of anything is just the positive version of it. So the absolute value of negative 3 is 3. The absolute value of positive 3 is
3.
3. Positive 3. I heard a negative 3. Remember, it doesn't mean you get the opposite sign. It means, woo, just pay attention. It doesn't mean it turns into the opposite sign. It means it is always going to be positive, okay? Now, graphing this is very interesting. Sometimes it's really hard to graph unless they give you more information about what your x-axis and what your y-axis should represent. That's a little bit tricky. So I'm going to help you guys with this. So we're going to allow our x-axis as our mile markers, meaning the distance from mile 1 all the way to mile 8. And that would include all of the miles in between, right? Mile 1, 2, 3, 4, 5, 6, 7, and 8, right? So if I'm going to graph this, my domain, or my x values, would be my mile markers. From mile 1 to, or I should say from mile 0. This would be mile 0, right? Mile 0 to mile 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, are we going to make points for each of these mile markers? No, just for the specific groups, because there's no group starting at mile 7, there's no group starting at mile 4, but those distances do exist, right? Stop. Okay? Now, if these are my mile markers, and this is a really tricky question, let's see if we can get this. What will this represent? If you want a hint, go to B. It says make a graph that relates the position of each group on the trail to their distance from the waterfall. Distance from the waterfall. Very good. They're just so hard to catch. You slip right through. Okay, so this is our mile markers. And here is our distance from waterfall. Now the distance from the waterfall, we noticed that what was the maximum distance from the waterfall according to our little picture here? The maximum distance, or I should say, which group is the maximum distance away, and what distance was that?
8.
Yes, 8 was the maximum distance, and that was a distance of how many miles?
3.
3. So we don't really need to go. Oh yeah, sure.
Perfect. Thank you so much.
No problem. So, oh, sorry. All right. So since our distance between our groups and the waterfall isn't higher than 3, I don't really need to go higher than 3. So I'll just go like this. 1, 2, 3. Actually, I'll go up to 4 just because I want to. I'll even go up to 5 just because I want to show you something after that. Okay? So, what would the coordinates of starting from this side, what would the coordinate of mile 2 be?
2.
2 what?
Y? No, X.
2 on our X, and then what would it be in terms of the Y value, the distance from the waterfall? 3.
They don't.
3.5.
You said 3. 3. Very good.
Why is it 3?
It's 3 because as we were looking at earlier, the distance between mile 2 and the waterfall, this is like where they're trying to go.
Oh.
The distance between mile 2 and the waterfall is 3. So if the group is at mile 2, they are 3 miles from the waterfall. Now let's look at the group that's at mile 5.
No,
How
yeah,
far
0.
are they from the waterfall?
0,
0. Well, not 0, 0. They're at mile 5.
5-0.
5-0. Very good. Okay. Now, what about the group at mile 6?
6-1.
6-1. Very good. Do you guys
Excellent.
understand how we're getting the Y value? If it's the group at mile 6, they are 1 mile from the waterfall. That's their distance. So 1 mile from the waterfall, 6-1. Okay. And 7, we don't have anybody there. Mile 8.
3.
3, very good. You guys are
Boom,
totally getting this
shakalaka.
lesson and we haven't even gotten to the full example. So 8-3. Now, this is a really weird graph. It's not linear. Okay, this is not a linear function. It's an absolute value function. Watch what happens when I connect the dots from left to right. So I'm starting here. My next dot is all the way down here. So when I connect it, and then my next dot going over is up here.
It's like a check mark.
And then my next dot is up here. These are kind of supposed to be the same level. I just kind of did the dot a little too high over here. It's not a perfect graph.
Oh, no, it's like B.
Yes, it looks like a V. Now, why does this V have only 1 dot over here, but it has 2 dots over here?
Because it's not linear.
No. Why is there, how come I don't have a dot over here? Like, why doesn't it match?
Because all the
Because there's more
There.
mile-like things.
Right, because there are 2 groups on this side of the waterfall and only 1 group on that side. So all we have plotted was representing the groups, but in terms of the distances, let's see if everything else will follow in this. No. Nope. Don't look at your friends, it doesn't matter if they started it. Why would you do it? Do you regret everything?
Yep.
Are you sorry?
Yes,
It's
ma'am.
not gonna happen again, right? And friends in the back? It's not gonna happen again,
I
right?
didn't even do it.
It doesn't
That's
matter.
cat.
You just yes ma'am and we move on.
Matter of fact, I just lost my legs.
Got it?
Yes, ma'am.
Thank you. All right, so if we have other groups, let's pretend there are more groups. What about mile 0? How far would that be?
5
It would be
miles.
5 miles. That would be the distance to the waterfall. So mile 0 would be all the way up here at 5 miles. What about mile 1?
4.
Would be 4 miles. And look how they connect in that perfect V. Now what about mile 3?
2.
2 miles. What about mile 4? Are you guys sensing the pattern here?
Yeah.
Okay, then we have 5 and 6. And what about mile 7? 2 miles. And then we have mile 8. And then we could go 9, 10, 11, 12. Okay. And we see that this absolute value function would just continue like this, right? This kind of large V shape. Yes? Did you hear me in the beginning saying if you have to go to the bathroom, go now, because we're not going to the bathroom during the lesson because we're going to miss really important information, okay? So you can wait until the end. All right, so do you guys totally get that this is an absolute value function? Absolute value functions make a V shape. Sometimes they're facing upwards like a V, and sometimes the V is flipped downwards. We'll talk about that in a little bit. But that's really the whole concept of the lesson. That, oh, there's one more thing I want to say before we move on. Do you know what this is called here, where the V or any two, what? Vertex is correct. Any two lines that form a corner, that's called the vertex.
Watermelon, my favorite.
You'll notice that the vertex is kind of the place, if I were to draw a line straight through that vertex, I'm causing something, it starts with an S. I want to see if you guys can get it. Yes?
Symmetrical balance.
Yeah, it's causing symmetry. There is symmetry. This line is a line of symmetry. And that creates, if you picture this as like a piece of paper and you kind of fold it there, it's going to line up. Like a heart would or like a butterfly would. It's symmetrical.
Yeah.
So an absolute value function is symmetrical. All right, let's see. And the line of symmetry for this one would simply be called x equals 5. That would be its line of symmetry for this function. I think that's all I want to say about that. But that was, I really like this example as the do now because I think it really gets you guys understanding the lesson before I even go through the other examples. So great job. Okay, so now it gets a little looks more complicated, but I promise it's not. It's the same thing we just did. So the question is, this is the essential question for the whole lesson. What are the key features of the graph of the absolute value function? Key features is just like, how can we describe the most important parts of this function? What do you think a key feature might be when we're describing a function?
Like the outcome.
Yeah, output, which we would call the
X or Y.
Y or the
Range. X, no.
Range.
range. Very good. So a key feature would be the range, absolutely. What would another key feature be?
Domain.
Domain, very good. So we're gonna look at all the different features of this function. This function is a very, very simple absolute value function. It's so simple that the only thing that's happening, Jayla, that's not what we're doing right now. No guys, stay forward. I don't want to take time away from the lesson, but do you think that I can't see what you're doing, or do you just not care that you're up? It's just that you know that you're not supposed to be doing that, right? So if you know that you're not supposed to be doing something and your teacher can see you, don't do it. That's the decision that you need to make for yourself. So I don't need to get parents involved and tell you to go to Mrs. Room. I don't want to do that. Let's just handle ourselves the way we're supposed to handle ourselves. And let's get back to the lesson and not waste any more time. Okay, so this function, what's happening to x? There's only one thing happening to it. What does that symbol mean? Where the little prism bar is?
Absolute value.
Yeah, absolute value. So they're saying the output is going to be whatever the absolute value of x is. whatever number you put into the machine's gonna absolute value it and spit it out. So if I put a 3 into the machine, what's gonna come out?
3.
A 3. If I put a -7 into the machine, what's gonna come out? If I put a +7 into the machine, what's gonna come out? Good, you didn't fall for the trap. So anything that goes in comes out the positive version, not the opposite sign version, the positive version. When you are making a table of values, meaning let's get some coordinate pairs that will allow me to graph this function, you're going to always want to choose values that include some negatives and some positives, because that's what's going to allow us to have that V shape on our function. If you only include like a 0 and then your positive values, you're just gonna get that one side of the V and it's gonna look like a line, but it's not a linear function. You need negative inputs to really see the full function. Now what's cool is on your homework for this, which isn't due until Tuesday, you really only need to plot 2 points of your absolute value function. The only points you need to plot are the vertex and then one other point on either side of that V, and then it just automatically plots the V for you. But here we're going to really kind of look at every point that we're getting from this table. So the function f of x equals the absolute value of x simply means take a number, put it into the machine, and see what comes out. So our input is -2. When it gets absolute valued, it becomes a +2. And that's our coordinate pair. -2, +2. So let's look over here. -2, +2. That's our first point. And then we keep going. Now we put in a -1. Our input, our x value is -1. It comes out a +1 because it's an absolute value machine. It comes out a positive value at 1, so we have -1, +1. -1, +1. You guys see a pattern here? When you put 0 into an absolute value machine, it's just going to come out a 0, right? Because 0 is neither positive nor negative, so it's just going to come out a 0. So our point here is the origin, 0, 0. Does that make sense? Now, if you only plotted those numbers, you wouldn't have that and it'll just look like a line, and that is not an absolute value function. You need more values. What about a +1? If that goes into the absolute value machine, it's going to come out a +1. Yes, so it's just 1, 1. If you put in a 2 to the absolute value machine, it spits out a 2. Very good, you can have your notebook out, please. Notebook out and open. It's going to spit out a 2, so we have +2, +2. And then we connect our little dotty dots. And we put arrows because it's continuous. There are more values. I could put a -3 here and a +3, a -6 and a +6, a -1 million and a +1 million. I'm not going to want to graph that, but I could if I wanted to. That's why we have those arrows, to represent all of those values that we don't actually feel like graphing because it will take too long. But we see our function, and now we can see different parts of the function. One thing that we're noticing is the vertex is at the origin. Very good, our vertex is 0, 0. That's the point where the axis of symmetry is. So our axis of symmetry cuts through the vertex and creates some symmetry of the function. You could fold it on the axis of symmetry and it would match up perfectly. Does that make sense? So far this isn't too hard, right? So we went from linear functions where we just did lines, now absolute value functions where instead of continuing down, it goes burp and then goes back up because the absolute value is spitting out positive versions of everything. So notice how, what is missing down there? We don't have any y values down there. So there's a restriction on our range, right? I think it's gonna ask that in the next question, let's see. There it is. Let's do this together. What is the domain, or what are the domain and range of that function that we just did? Let's go ahead and look at the graph. If you ever get a question like this and it doesn't show you a graph it. Make a table of values. Just do -2, -1, 0, 1, 2. Or just do -1, 0, 1. Even if you just do those, you'll get a V and you'll be able to see your range and your domain very easily. Oops, let's go back and let's look and identify our domain and our range. What is domain? X values. So we're looking along this x-axis. How many values of our x
4.
are included in all of the points on this function? Yes.
4.
Just 4? What about if I make another point here, and 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 another point here? And what if I go forever over here? And what if I go forever over here? Now it looks like it's getting further away from the x-axis, right? But it's not about how close it is to the x-axis. It's about, look, this x-axis continues too. So any point that's all the way up here is going to have an x value and a y value, but it will have an x value. So even if it continues to positive 1 trillion, it will have the x value of 1 trillion, right? And same going back there and even further and further to numbers that I don't even know the names for. So what does that say about the domain of x?
It's
all real
infinite.
numbers.
Very good.
It's all real numbers.
Yes, it is all real numbers. He's right, it goes to positive infinity, it goes to negative infinity, and the way that we can kind of concisely say it is that x is all real numbers, or the other way to say it is x is a real number. And I know that sounds like, but then you're just saying it's one real number. We're saying x is any real number. So the domain would be x is a real number. Or you could say x is all real numbers, the same, that means the same thing. That's our set builder notation. Now let's talk about the range. Remember how we were saying there was a restriction on the range? Give me a value of the range, give me a value that could not be included in the range.
What?
Give me a value that could not be
Zero.
-1 is a good one. 0 is included because at the origin, we have the points 0, 0. So 0 on the y, that's included.
-2.
-2.
-3.
-3. Any negative number. Very good. So there are a couple of ways to explain that, right? We could say y can be anything except for negative real numbers, right? We could say we could say y has to be positive, and but it could also be, y can either be positive or it could also be, no, it can't be negative, remember? What number is neither positive nor negative?
0.
0. So it can be 0 or all the positive numbers. How do we write that in a very concise way? It starts with an I. And what? No, because it goes to positive infinity, but we can't say that y is infinite. It has a restriction of it cannot go lower than 0, right?
Integral?
No. Yeah.
Y is greater than 0.
Or
Y
Equal to.
Very good.
Just
What do we call that? It starts with an I.
inequality.
An inequality, very good. So the range is y. Y is greater than or equal to 0. So we can use an inequality in our set builder
What do you
notation.
think was a jolly
I
range?
got inequality right, so like that's.
Did you say inequality first before anybody else
Yeah.
I mean, me and Aiden kind of said that at the same time.
at the same time?
Yeah, so we should both
Okay.
get one.
I like how you guys like tell me, like, oh, I need a Jolly Rancher. I said it. All right, so that's it for this example. Let's go on to the next one.
Watermelon again, my favorite.
Are you, do you feel like you're getting it? Kind of. Are you going down or are you?
Just being down.
All right, we're gonna get through about half of this example, maybe a little bit. Oh yeah, we'll get through more than half of it. But we need silence.
Yes, ma'am.
Okay. So now we're looking at the difference between these two absolute value functions. They're on the same graph. One is outlined in black. It just happens to be the exact same one that we just did, right? The function of x is the absolute value of x. Same exact points that we just had in this problem, right? So in -1, 1, -2, 2, -1, 1, -2, 2. It just goes on a little bit further, but it's still following that same function. So f of x, same exact function that we just worked with. Absolute value of x equals your output. Now we're going to compare it to an absolute value function that takes the absolute value of x and then multiplies it by 2. So now, Jayla, we have a different machine. Are you writing down this? Can I see it? Okay, so don't lie to me, okay? If I ask you, just say, no, I'm not, and I'm sorry, I'm gonna pay attention this time. Okay, so this function is kind of taking this, it's like stealing the idea from this machine, and it's like, yeah, that's cool and everything, to absolute value x, but I'm gonna do something else. I'm gonna take the absolute value of x, and then I'm gonna multiply it times 2, and then I'm gonna see what function y looks like, okay? And then when that gets graphed, look, let's just go ahead and put in like -1, 0, and +1, okay? And we'll see what, okay, that's my input, that's what I'm putting in for my x. Let's see what the output would be. So g of x. If I put -1 into here, it's gonna be 1 times 2, which is 2. If I put a 0 in, it's gonna be 0 times 2, which is 0. And if I put a 1 in,
2.
it's going to be 1 times 2, which is 2. Okay, let's just make sure that matches up. -1, 2. -1, 2, that's good. 0, 0, they're both hitting the origin. And then I have +1, +2, that's good. And then we can see that if we continue those lines, they're going to keep going and going and going. I could expand my table, but do I need to? Or do I?
Like +1 million and +2 million.
Totally could put it on there, but since we don't have enough space, I'm gonna skip that part. But we do see in our minds that we can go that far, okay? So, are these both absolute value functions? Yes. Are they the same function? Are they both, like, do they kind of look alike? Yeah, kind of, but they're not exactly alike, so there's just a little bit different. It's funny, this absolute value function is a little bit of a wider v. This one, when you multiply it by 2, it kind of compresses a little bit, right? Just something to notice. Now it says, how do the domain and range of these functions compare? Are they are the domains the same or are they different? Are the ranges the same or are they different? And if they are different, how? Let's see. What did we say the domain was for our original function? Real numbers, right? The domain was real numbers. And what did we say the range was?
All positive real numbers.
No, 0.
How did we write that? Y is?
Oh, y is greater than or equal
Yeah.
to 0.
Good. Y is greater than or equal to 0. Now look at this. What is our domain going to be for the red function?
All real numbers.
All real numbers. Very good. And what is the range?
For the black one,
The red one.
For the red one.
y is greater than or equal to 0.
Very good. Very, very good. You are just like so on it today. Not paying your dentist bill, by the way, with all this candy. I'm not responsible for all the cavities you guys are getting. Teacher joke. All right, stop.
Not responsible for
Okay. I'm not the tooth fairy.
I'm in Nebraska.
Okay.
This one.
All right, so we see that there actually isn't a difference. So what we would basically say is the domain and the range of these two functions are the same. They look different, but they have the domain and range in common. Now, it says, let's see. That's it. Let's go to this next part. You okay, Lathan? You gonna be okay? Oh my goodness, it did a flip. We have our original function, and then he did a little flippy. Where did he do his flippy? Over the
Negative. Or positive.
over the
Oh, X.
x-axis. Yes, he did a little flippy. We call that, it starts with an R.
A reflection or something like that.
Yeah, it's a reflection or something like that. It's exactly that. It's a reflection. Good. So this did a little flippy over the x-axis, and it kind of makes sense, right? Because this function,
Can't you just say it can't be negative? You were just saying it can't be negative.
oh, if the absolute value of a number can be negative, but if I take the absolute value of a number, which is positive, and then multiply it times a negative, it will become a negative. So good question. This is an example of a function it's basically this function being like, yeah, that's cool. Now all you think you're so cool, making everything positive, but my machine is then gonna turn it negative. So it flips it. So now all the values that were positive on the y are now going to be negative on the y. So this is the function. We can make a function table for it and make sure it's lining up, but I think we can kind of believe it, right? Or can we? I'm not really sure. The graph of function h is a reflection of function of x over the x-axis. Now this is interesting. Over what intervals is h of x positive? Over what intervals is h of x positive? Well, do you see any possible positive
Nope.
values for h?
No.
Nope.
No, there are no positive values for on the y values. So we would say that it is never going to be positive. Now, you guys okay? Over what intervals is h negative? Now this is interesting. Over what intervals is h negative? It looks like all of the intervals, right? It looks like every x value will give a negative y,
But zero.
except for 0.
Zero is not positive or negative.
Yes, except for 0. So this is the way that it's written. It says the function h is negative for values where x is not 0. This is the only point that doesn't give negatives. So it's negative for the values, all the values, except when x equals 0. And that's the opposite of this, because the function of x is never negative. It's always positive unless it equals 0. So it's positive except for when x equals 0. You guys understand? You guys can pack up and go. Make sure can you stop the video?